Early October 1944, Kummersdorf Proving Ground, Brandenburg, Germany. The captured 76mm round sat on the examination table under harsh fluorescent lighting, its aluminum body still scarred from impact against armor plate. Oberingenieur Werner Ossenberg adjusted his calipers, measuring the diameter of the strange subcaliber penetrator core that protruded from the shattered projectile body. 2.4 centimeters. Far smaller than the 76mm bore that had fired it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The material was unmistakable to anyone trained in metallurgy. Tungsten carbide. Dense, hard, and in German hands, critically scarce. This single round, recovered from a disabled Panther near Aracourt 3 weeks earlier, represented a technological shift that German tank designers had feared but hoped would never materialize. The Americans had solved the Panther problem not through superior armor or bigger guns, but through industrial chemistry and metallurgical engineering applied to ammunition design. The mathematics were already forming in Ossenberg's mind as he weighed the core section. If the Americans could produce tungsten carbide ammunition in meaningful quantities, the carefully calculated protection margins that made the Panther Germany's answer to Allied numerical superiority would evaporate. The frontal armor that had kept German crews alive, the sloped glacis plate that deflected every standard American 75 and 76mm round, suddenly possessed a vulnerability that competent enemy gunners could exploit. The gun mantlet, necessary for the main gun to elevate and traverse, had become a death trap. What Ossenberg and his team of ballistics specialists would document over the following weeks would trigger a crisis of confidence that echoed through German armored vehicle design bureaus for the remainder of the war. Not because German engineers lacked understanding of tungsten carbide penetrators. Germany had pioneered such ammunition years earlier, but because American industrial capacity had produced specialized armor-defeating rounds in quantities that German factories, starving for strategic materials and reeling under Allied bombing, could never hope to match. The testing program about to begin would prove what German tank crews were already reporting from the front. American Shermans, previously dismissed as inferior opponents to be defeated at leisure, had acquired teeth sharp enough to kill Panthers. The story of how German engineers confronted this new reality begins not with the round itself, but with the battle reports that had been arriving from France throughout September 1944, each one more troubling than the last. Reports that described Sherman tanks achieving frontal penetrations on Panthers at ranges previously considered safe. Reports that mentioned smaller entry holes than standard American ammunition produced. Reports from Panzer commanders who suddenly found themselves ordering more cautious tactics when facing an enemy they had been trained to consider technically inferior. September 26, 1944. Army Group G Headquarters, Molsheim, Alsace. The intelligence summary from 5th Panzer Army made grim reading for anyone responsible for German armoured operations in the West. The 113th Panzer Brigade, equipped with brand-new Panther tanks straight from German factories, had been effectively destroyed in 11 days of fighting near Aracourt. Of approximately 90 tanks and assault guns that entered combat on September 18th, fewer than 20 remained operational by September 29th. The kill ratios defied expectations. American forces reported destroying 86 German tanks and assault guns, while losing 25 Sherman tanks, 7 tank destroyers. The 4th Armoured Division, which had opposed the German attack, fielded primarily standard 76mm Shermans, not the specialized tank destroyers with 90mm guns that German intelligence had learned to fear. Something had fundamentally changed in the tactical equation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The preliminary after-action reports from surviving Panther commanders painted a confused picture. Some reported that American tanks were firing rounds that produced bright flashes on impact, different from the characteristic sparks of standard armor-piercing shot bouncing off armor. Others described penetrations through the gun mantlet at ranges exceeding 500 meters, distances where American 76mm guns should not have been able to defeat cast steel armor over 100mm thick. Several commanders reported hearing rumors that the Americans had secretly deployed British Firefly tanks with 17-pounder guns, though no visual confirmations supported this theory. Oberst Heinrich Freiherr von Luttwitz, commanding the 2nd Panzer Division, submitted a detailed technical query to Army Group G headquarters on September 28. His unit had examined 2 disabled Panthers that showed unusual penetration characteristics. The entry holes were notably smaller than the 76mm bore diameter would suggest. The penetration channels through armor showed smooth walls without the rough fracturing pattern that steel shot typically produced. Most tellingly, unexploded American rounds recovered near one disabled Panther appeared to contain a sub-caliber core made of extremely dense material, possibly tungsten carbide. This last detail triggered immediate concern at the Army Weapons Office in Berlin. If accurate, it meant American industry had deployed tungsten core ammunition to frontline tank units. Not experimental rounds for testing, not limited issue to specialized tank destroyer battalions, but regular issue to ordinary Sherman tank companies engaging German armor across the front. The German army had developed its own tungsten core ammunition, designated Panzergranatwerkzeug, in 1940. The round used a tungsten carbide core in a lightweight steel carrier, achieving significantly higher penetration than conventional armor-piercing shot through increased velocity and concentrated kinetic energy. The Panzergranatwerkzeug had proven devastatingly effective in testing and limited combat employment, but tungsten supplies in Germany were never adequate to support mass production. By late 1944, German tungsten stocks were reserved almost entirely for machine tool production, critical for manufacturing aircraft engines and precision components. Tank gun ammunition received vanishingly small allocations. Most Panther crews had never seen a Panzergranatwerkzeug round, let alone fired one in combat. The entire German armoured force fought with conventional ammunition, while knowing that far more effective tungsten core rounds existed but could not be manufactured in meaningful quantities. If Americans possessed similar ammunition and could produce it at scale, German advantages in armour protection and gun performance would be significantly degraded. The Panther's carefully engineered frontal protection, designed to defeat all known American tank guns at normal combat ranges, would become vulnerable to a threat German designers had not anticipated. American industry could deploy widely. The Army Weapons Office issued explicit orders on September 29. All units encountering unusual American ammunition were to recover samples immediately and ship them to Kummersdorf for comprehensive analysis. Tank crews were instructed to search disabled American vehicles for unfired ammunition and document the characteristics of any penetrations that appeared inconsistent with known American projectile types. Priority 1 classification. Results needed for immediate assessment of operational implications. The first samples arrived at Kummersdorf on October 2nd, transported by special courier from France. 3 complete rounds, recovered from a destroyed Sherman near Aracourt. 4 fragmented projectiles extracted from disabled Panthers. 2 unexploded rounds found embedded in armor that had stopped them after partial penetration. Each item was photographed extensively, measured precisely, and catalogued with meticulous German thoroughness before testing began. The examination of the complete rounds revealed American engineering philosophy applied to a problem German designers knew intimately. The projectile consisted of a tungsten carbide core, roughly 2.4 centimeters in diameter and 11 centimeters long, surrounded by an aluminum alloy body that brought the overall diameter to 76 millimeters. A lightweight aluminum ballistic cap covered the nose. The total projectile weight was approximately 5 kilograms, significantly lighter than the standard M62 armor-piercing round that weighed 6.3 kilograms. This weight reduction, achieved by substituting lightweight aluminum for steel in the carrier body, allowed substantially higher muzzle velocity. The propellant charge was identical to standard 76mm ammunition, but accelerating a lighter projectile produced velocities approaching 1,050 meters per second at the muzzle. The standard M62 round achieved only 792 meters per second. This 258 meter per second velocity advantage translated directly into kinetic energy available for armor penetration. The tungsten carbide core itself represented excellent metallurgical practice. The material possessed a Vickers hardness exceeding 1800, making it one of the hardest substances available for industrial applications. The density of 15.6 grams per cubic centimeter meant that the relatively small core contained substantial mass concentrated in minimal volume. Upon impact with armor, this dense, hard core would punch through steel plate like a drill bit, carrying its kinetic energy through the armor to the vehicle interior. German engineers recognized immediately that American designers had optimized every aspect of the projectile for maximum armor penetration. The lightweight carrier maximized velocity, the dense tungsten core maximized energy concentration. The streamlined shape minimized aerodynamic drag to preserve velocity over distance. Even the aluminum construction of the carrier body served a secondary purpose. Aluminum produced less barrel wear than steel, allowing higher velocities without excessive gun tube degradation. Werner Osenberg prepared a preliminary technical report for circulation to Army Group commanders and the Armaments Ministry. The document, classified as secret and distributed on October 5, outlined the basic characteristics of the American round and provided initial penetration estimates based on calculated kinetic energy. The assessment was sobering. Against homogeneous armor plate at 0 degrees obliquity, meaning perpendicular impact, the American round would penetrate approximately 160 millimeters of armor at 1,000 meters range. Against cast armor, typically 20% weaker than rolled plate, penetration would be even greater. The Panther's gun mantlet on the OSF D and A variants was 100 millimeters of cast steel. The OSF G variant, now in production, had increased mantlet thickness to 120 millimeters, after earlier combat experience revealed the vulnerability. Neither thickness would reliably stop the American tungsten round at normal combat ranges. The mantlet, a necessity for gun operation, had become an Achilles heel that competent enemy gunners could exploit. The implications cascaded through German armored vehicle design philosophy. The Panther had been conceived as a medium tank that could engage Soviet T-34 tanks effectively while possessing frontal armor protection sufficient to resist most enemy anti-tank weapons. The sloped 80mm glacis plate, positioned at 55 degrees from vertical, created an effective thickness of approximately 140 millimeters against projectiles striking perpendicular to the surface. This protection scheme had proven highly effective against Soviet 76mm guns and American 75mm guns throughout 1943 and early 1944, but the protection scheme contained an inherent weakness. The gun mantlet could not be sloped as dramatically as the glacis plate. The gun needed to elevate and depress, requiring a curved mantlet that allowed this movement. The mantlet's thickness had to balance protection with weight, as excessive mass in the turret front would overload the turret ring and make traverse difficult. German designers had calculated that 100mm, later increased to 120mm, provided adequate protection against known American tank guns. Those calculations were now obsolete. The American tungsten round rendered the carefully engineered protection margins insufficient. A Sherman 76 equipped with these specialized rounds could now achieve frontal kills on Panthers at ranges up to 1,000 meters by targeting the mantlet. This completely changed the tactical dynamic that had favored German armor throughout the summer of 1944, October 8, 1944, Kummersdorf firing range. The comprehensive testing program began with live-fire trials against representative armor samples. German engineers had prepared test targets using actual Panther mantlets removed from damaged tanks returned from the front for salvage. 3 mantlets from OSF D Panthers with 100mm thickness, 2 mantlets from new production OSF G Panthers with 120mm thickness. Each would be mounted in test fixtures at ranges from 200 to 1,200 meters. The firing platform was a captured American M4A3 Sherman, taken intact during the Ardennes offensive earlier in the year and maintained in operational condition specifically for ammunition testing. German crews had fired hundreds of rounds through this particular Sherman, documenting the performance of various American ammunition types. The 76mm M1 gun was thoroughly understood. What remained unknown was how the tungsten core rounds would perform under controlled conditions that allowed precise measurement and documentation. The first shot was fired at 200 meters against an OSFD mantlet. The tungsten core penetrated cleanly, producing an entry hole approximately 2.5 centimeters in diameter, with smooth walls showing minimal fracturing. The core traveled completely through the 100mm thickness and impacted the backing plate positioned 1 meter behind the mantlet to simulate the interior arrangement of a Panther turret. The backing plate, 20mm mild steel, was perforated easily. Fragments and spalling would have killed or wounded the entire turret crew. Subsequent shots at 400, 600, and 800 meters produced similar results against the OSFD mantlet. Clean penetration, minimal energy lost to fracturing the armor. The tungsten core retained sufficient energy after penetration to be lethal to crew and equipment inside the turret. Even at 1,000 meters, the maximum range tested, 4 of 5 shots achieved complete penetration. 1 round struck at an oblique angle and deflected, but the other 4 punched through the cast steel, the mantlet, as if it were only mildly resistant to their passage. The OSFG mantlets, 20mm thicker, performed marginally better. At 1,000 meters, only 2 of 5 shots achieved complete penetration. The other 3 rounds penetrated partially, creating deep craters in the mantlet interior surface but not breaking through completely. However, even these partial penetrations would likely have disabled the gun by warping the mantlet or jamming the gun mounting. And at ranges below 800 meters, the OSFG mantlet was penetrated reliably with every shot finding its way through the cast steel. The testing confirmed what preliminary calculations had suggested. American tungsten core ammunition transformed the 76mm Sherman into a credible threat to Panther frontal armor within normal combat engagement ranges. German crews could no longer rely on simply keeping their front toward the enemy. They needed to consider the mantlet as a critical vulnerability that required concealment or tactical positioning to protect. Additional testing explored penetration against the glacis plate, the heavily sloped frontal armor that formed the Panther's primary protection. The results here were far more favorable to German armor. The extreme slope, 55 degrees from vertical, meant that projectiles struck at very high obliquity. The tungsten cores, though hard and dense, were also brittle. High obliquity impacts against sloped armor often caused the cores to shatter on initial contact rather than penetrating. At ranges beyond 600 meters, the glacis plate consistently defeated the American rounds. The cores struck the sloped surface, shattered from the impact angle and high hardness of the armor, and deflected without achieving penetration. Even at 400 meters, only 1 in 3 rounds successfully penetrated the glacis. The extreme slope proved highly effective at defeating even specialized armor-piercing ammunition. This finding provided some comfort to German tankers. The glacis remained a reliable defense if Panthers could be positioned to present this armor to enemy fire. But combat conditions rarely allowed such ideal positioning. Tanks maneuvered constantly. Terrain features and tactical situations forced movement that exposed side armor or created angles where the glacis could not be presented perpendicular to enemy guns. And the mantlet remained vulnerable regardless of positioning, a permanent weak point in otherwise formidable armor protection. The psychological impact on German crews would be severe, testing officers noted in their reports. Panther crews had been trained to trust their frontal armor. Doctrine emphasized using the armor advantage to close with enemy tanks and destroy them with the superior WWII 42 75mm gun that could penetrate Sherman armor at ranges exceeding 2,000 meters. This tactical approach assumed German crews could advance confidently, trusting their armor to protect them from return fire until they reached ranges where their gunnery superiority would be decisive. American tungsten rounds undermined this entire tactical framework. Panther crews now faced enemies who could achieve kills at ranges where German doctrine assumed safety. The gun mantlet, always present and always vulnerable, meant that even hull-down Panthers exposing only the turret were at risk. German tank commanders would need to adopt more cautious tactics, using terrain more carefully and avoiding exposures that allowed American gunners clear shots at the mantlet. But defensive tactics surrendered initiative to the enemy. American forces, with their overwhelming advantages in artillery, air support, and logistics, excelled at combined arms operations, where German armor was forced to react rather than dictate the terms of engagement. Making Panthers more cautious and defensive played directly into American operational strengths. October 15, 1944. The comprehensive test report was completed and distributed to senior Wehrmacht commanders, the Armaments Ministry, and tank design bureaus at Daimler-Benz, MAN, and Henschel. The document ran to 47 pages, including detailed photographs of test results, penetration tables at various ranges and angles, and technical analysis of the American projectile design. The conclusions section made for grim reading. The American M93 HVAP round, as German intelligence had identified it, could reliably penetrate Panther gun mantlets at all combat ranges up to 1,000 meters. The glacis plate remained generally proof against the round except at close ranges and favorable angles, but combat conditions frequently prevented ideal armor presentation. Side armor, only 40 to 50 millimeters thick, was completely vulnerable to tungsten core ammunition at all ranges. The report estimated that American tungsten ammunition increased Sherman's 76mm effectiveness against Panthers by approximately 300% compared to standard M62 armor-piercing shot. This did not make Sherman tanks equal to Panthers in direct comparison. The Panther's superior gun could still kill Shermans at twice the range that Shermans could threaten Panthers, but the margin of superiority had narrowed dramatically. American crews now possessed ammunition that gave them reasonable odds of achieving kills if they could close to combat ranges and place accurate fire on vulnerable points. Most troubling was the section addressing production capacity. German intelligence estimated, based on recovered ammunition and prisoner interrogations, that American industry was producing several thousand tungsten core rounds monthly by late 1944. Distribution prioritized tank destroyer battalions, but regular Sherman tank companies were receiving small allocations, typically 5 to 6 rounds per tank. This meant that in any major engagement, American forces would have dozens or even hundreds of tungsten rounds available. German tungsten production, by comparison, was essentially zero for ammunition purposes. All available tungsten went to machine tool manufacturing and specialized applications where no substitute existed. The German armored force fought exclusively with conventional ammunition, despite having developed tungsten core projectiles years before the Americans. German crews knew that superior ammunition existed but could not obtain it. American crews were being supplied, albeit in limited quantities, with exactly the specialized ammunition they needed to defeat German armor advantages. The disparity in industrial capacity was starkly evident. American factories produced tungsten ammunition while simultaneously producing thousands of tanks, hundreds of thousands of trucks, unlimited artillery ammunition, and maintaining Lend-Lease shipments to Allies. German factories struggled to produce enough tanks to replace combat losses, faced constant shortages of every critical material, and operated under the threat of Allied bombing that could destroy months of production in a single night raid. The report concluded with recommendations for tactical doctrine and future tank design. In the near term, Panther crews needed updated training emphasizing terrain use and tactical positioning that protected the gun mantlet. Hull-down positions that exposed only the turret were no longer safe and should be avoided when facing American 76mm tanks. Panthers should engage from maximum range where their gun superiority remained decisive, avoiding close-range engagements where American tungsten ammunition was most effective. For future designs, the report recommended either eliminating the gun mantlet vulnerability through redesign or accepting that medium tanks would be vulnerable to specialized ammunition regardless of armor thickness. Designing armor protection sufficient to defeat. Tungsten core ammunition at all angles would require weight increases that would make vehicles slow and mechanically unreliable. Better to accept some vulnerability and compensate through tactical skill and superior gunnery. These recommendations, thoughtful and grounded in solid engineering analysis, arrived far too late to influence German tank production meaningfully. The Panther OSV-G, already in production, represented the final evolution of the design. No fundamental redesign would be undertaken. The Panther would fight for the remainder of the war with a known, exploitable vulnerability that American crews were learning to target effectively. November 1944 brought additional samples of American ammunition to Kummersdorf as Wehrmacht forces retreated across France and struggled to contain Allied advances. Engineers examined HVAP rounds for the 3-inch M7 gun used in American tank destroyers. These rounds, designated M79, used the same tungsten carbide core principle, but with larger dimensions appropriate to the bigger gun bore. Testing showed even more impressive penetration, capable of defeating Tiger frontal armor at normal combat ranges. The American ammunition development program clearly encompassed multiple calibers and priorities. Tank destroyers received the most capable ammunition. Medium tanks received sufficient quantities to make them credible threats. The systematic approach reflected an industrial planning capability that Germany simply could not match. American ordnance departments identified requirements, developed solutions, and scaled production to useful levels within months. German development programs took years and often never reached meaningful production due to material shortages and industrial limitations. By December 1944, when German forces launched their surprise offensive in the Ardennes, Panther crews were acutely aware of the American tungsten ammunition threat. Intelligence. Briefings before the offensive specifically warned crews that American Shermans possessed specialized rounds capable of frontal penetration. Commanders emphasized maximum range engagements and careful tactical positioning to minimize exposure to enemy fire. The Battle of the Bulge provided a massive real-world test of Panther capabilities against HVAP-equipped American armor under winter conditions that limited Allied air superiority. Initial German successes during the first days of the offensive demonstrated that Panthers remained formidable weapons when employed with tactical skill and surprise. But as American forces recovered from the initial shock and began coordinated counterattacks, the same patterns emerged that had characterized fighting throughout the fall. American armor, supported by devastating artillery fire and increasingly effective air strikes as weather cleared, engaged German tanks using combined arms tactics that negated Panther advantages. Sherman crews with HVAP ammunition targeted gun mantlets at ranges where German return fire was lethal, creating mutual threat situations rather than the one-sided engagements German crews expected. The psychological impact was evident in after-action reports. German tank commanders described American forces fighting more confidently and aggressively than in earlier engagements, pressing attacks even when facing Panthers that previously would have caused American units to call for specialized tank destroyers or air support. January 1945. Kummersdorf Proving Ground faced evacuation as Soviet forces advanced relentlessly toward Berlin. Testing programs were hastily concluded. Documentation was packed for shipment west. The captured Sherman used for ammunition testing was prepared for disposal, either to be destroyed in place or pressed into desperate defensive service if Soviet forces reached the facility before evacuation completed. Werner Osenberg supervised the final inventory of test data and prepared summary reports for preservation. Months of exhaustive testing had quantified precisely what German tank crews were experiencing in combat. American tungsten ammunition had fundamentally altered the tactical balance in ways that German industry could not counter. The data proved it mathematically. The test results demonstrated it visually, with neat holes punched through Panther mantlets that were supposed to provide protection. The battlefield reports confirmed it operationally, with Panthers being knocked out frontally by tanks they should have dominated. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical solution was obvious but impossible. Germany needed to redesign tank armor schemes to account for tungsten core threats, or develop and produce its own tungsten ammunition in quantities sufficient to maintain German gunnery advantages. Neither option was feasible. Armor redesign required time and production capacity that no longer existed. Tungsten ammunition required strategic materials that were unavailable and manufacturing capacity already overwhelmed by impossible demands. Germany had entered the war with technical advantages in many weapons systems and lost those advantages through industrial attrition. The tungsten ammunition story exemplified this pattern perfectly. German engineers developed the technology first, understood it thoroughly, and created functional designs. But German industry could not produce the ammunition in meaningful quantities. American industry, starting later with less theoretical knowledge, nevertheless manufactured tens of thousands of rounds and distributed them to frontline units where they directly influenced combat outcomes. The evacuation order came on January 23, 1945. Soviet artillery could be heard in the distance, growing steadily closer. Osenberg and his remaining staff loaded the final crates of test documentation onto trucks for transport west. The Panther mantlets used in testing, still bearing the neat penetration holes from American tungsten rounds, were left behind. No transport capacity existed for such bulky items of purely academic interest. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Soviet forces captured Kummersdorf on April 21, 1945, finding the testing facilities largely intact, but stripped of documentation and equipment. The examination ranges where German engineers had systematically documented American ammunition capabilities stood empty. The evidence of what had been learned there had been shipped west or destroyed, but the knowledge remained. German engineers understood precisely how American industry had overcome the Panther armor advantage. They simply lacked the capacity to respond effectively. The German response to American tungsten ammunition revealed the stark difference between theoretical knowledge and practical capability. Throughout late 1944 and into 1945, German tank design bureaus and ordnance offices struggled with a problem they understood completely but could not solve. The technical specifications for improved tungsten core ammunition existed in German files. The metallurgical knowledge was comprehensive. The ballistic calculations were precise. What Germany lacked was tungsten, production capacity, and time. The Heereswaffenamt, the Army Weapons Office, had maintained detailed records of tungsten consumption and availability since 1942. The statistics documented a steady decline in available supplies as the war progressed. In 1942, Germany had access to approximately 2,000 metric tons of tungsten annually through imports from Portugal and Spain, domestic mining of limited deposits, and stockpiles accumulated before the war. By 1944, imports had dwindled to a few hundred tons as neutral nations reduced exports under Allied pressure and German foreign currency reserves evaporated. Tungsten demand far exceeded supply across all applications. Machine tools for aircraft engine production consumed the largest allocation. These specialized tools, incorporating tungsten carbide cutting edges, were essential for machining the hardened steel components in aircraft engines. Without tungsten carbide tools, production of BMW and Daimler-Benz aircraft engines would halt completely. The Luftwaffe's desperate need for fighters and the Me-262 jet program demanded absolute priority for tungsten in aircraft production. Tank gun ammunition received virtually nothing. The calculations were brutally simple. Each Panzergranatwerkzeug round for the 75mm KBUK-42 gun required approximately 0.7 kilograms of tungsten carbide. Producing enough ammunition to supply each Panther with even 20 rounds would consume 14 kilograms per tank. With roughly 6,000 Panthers built during the war, full ammunition stocks would require 84,000 kilograms of tungsten, or 84 metric tons. This represented nearly half of Germany's total annual tungsten availability in 1944, and that assumed zero tungsten for any other application. The trade-offs were impossible. Aircraft engine production or tank ammunition. Machine tools for general manufacturing or specialized armor-piercing projectiles. Every kilogram of tungsten allocated to ammunition was a kilogram, unavailable for applications that kept German industry functioning. The Army Weapons Office had decided years earlier that tungsten would not be available for ammunition in significant quantities. That decision, driven by material scarcity and competing priorities, now left German tank crews facing enemies equipped with the exact ammunition type Germany had developed but could not produce. American tungsten supplies, by comparison, were abundant. The United States imported tungsten from China, which supplied 36% of global production, and from South American sources that provided additional thousands of tons annually. Domestic mining in Colorado, Nevada, and California supplemented imports. Total American tungsten availability exceeded 10,000 metric tons annually throughout the war, more than 5 times German supplies, even in the best years. This massive supply advantage allowed American industry to produce tungsten ammunition for multiple calibers simultaneously. The 76mm M93 HVAP for Sherman tanks, the 3-inch M79 for tank destroyers, the 90mm M34 HVAP for the M36 tank destroyer and M26 Pershing tank, smaller calibers for anti-tank rifles and aircraft cannon. American ordnance could allocate tungsten to ammunition production without compromising machine tool availability or industrial capacity. The production numbers told the story clearly. By March 1945, American factories had produced approximately 33,000 rounds of 76mm HVAP ammunition. German production of comparable Panzer Granatwerkzeug rounds for the 75mm KAK 42 gun totaled fewer than 2,000 rounds for the entire war. The disparity was roughly 16-1 in American favor, and that was just one caliber. Including all tungsten ammunition types, American production exceeded German output by more than 20-1. German tank crews understood the implications viscerally. They possessed tanks with powerful guns and thick armor, but they fired conventional ammunition while facing enemies equipped with specialized tungsten rounds that could defeat their protection. The psychological impact was severe and measurable in after-action reports that described increasing German caution and defensive mindset as the war progressed into 1945. Hauptmann Otto Karius, a highly decorated tank commander who survived the war and wrote extensively about his experiences, captured this psychological shift in his post-war memoir. He described the evolution from confident offensive operations in 1943 and early 1944 to increasingly desperate defensive battles, where survival became the primary objective. The knowledge that enemy ammunition had improved while German capabilities stagnated contributed directly to this change in mindset. Karius specifically mentioned engagements where his Tiger tanks, even more heavily armored than Panthers, faced American fire that penetrated frontal armor at ranges previously considered safe. While he did not explicitly identify the ammunition as tungsten core in his combat reports, post-war analysis confirmed that several engagements he described involved American HVAP rounds. The psychological impact of watching supposedly impenetrable armor be defeated by enemy fire fundamentally altered tactical decision-making for German crews. The tactical adjustments German commanders implemented in response to American tungsten ammunition revealed both professional competence and strategic desperation. Updated training materials distributed to Panzer units in November 1944 included specific sections on countering improved American ammunition. The guidance emphasized several key points that reflected accurate understanding of the threat characteristics. First, engage at maximum range whenever possible. The Quake 42 gun could penetrate Sherman frontal armor at ranges exceeding 2,000 meters. American 76mm guns, even with tungsten ammunition, were most effective below 1,000 meters. Maintaining engagement ranges between 1,000 and 2,000 meters maximized German advantages while minimizing American ammunition effectiveness. This required excellent range estimation, disciplined fire control, and terrain that allowed long-range observation and fields of fire. Second, use terrain to protect the gun mantlet. The training materials explicitly identified the mantlet as the primary vulnerability to American tungsten rounds. Panthers should position themselves to present the heavily sloped glacis plate to enemy fire, while keeping the turret masked behind terrain features when possible. Hull-down positions that previously were considered strong defensive postures now required more careful evaluation. If the turret was exposed, the mantlet was vulnerable. Third, avoid close-range engagements. German tank doctrine had traditionally emphasized closing with enemy armor to exploit superior gunnery and armor protection at ranges where German advantages were most decisive. This doctrine became suicidal against HVAP-equipped Shermans. Close-range combat negated German range advantages and maximized American tungsten ammunition effectiveness. Panthers needed to fight from distance, using their superior optics and gun performance to engage enemies before they could close to effective HVAP range. Fourth, coordinate with other arms. Panthers operating in isolation were vulnerable to combined arms tactics that American forces employed routinely. Infantry support could spot and suppress American tank destroyers. Artillery could disrupt American tank formations before they reached engagement range. Anti-tank guns could cover approaches that Panthers could not observe directly. The tactical guidance emphasized that Panthers, despite their impressive individual capabilities, could not operate effectively without combined arms support. These tactical adjustments were sound and reflected professional military thinking, but they were fundamentally defensive in nature. They prioritized survival over offensive action. They surrendered initiative to American forces who could dictate engagement, timing, and conditions through superior logistics and overwhelming material support. German armor, forced into cautious defensive postures by ammunition it could not match, became progressively less effective as an offensive weapon capable of disrupting enemy operations. The contrast with 1943 and early 1944 was stark. German armor during that period had operated with confidence that frontal armor provided protection and superior guns provided killing power at any engagement range. Panzer commanders attacked aggressively, closed with enemy forces, and exploited tactical opportunities without constantly worrying about being penetrated frontally by supposedly inferior enemy tanks. The arrival of American tungsten ammunition eroded this confidence and forced German crews to fight more carefully, more defensively, and ultimately less effectively. December 1944 brought the Ardennes offensive, Germany's final major attack in the West. The operation deployed nearly all available German armor reserves, including hundreds of Panthers and dozens of Tiger IIs, in a desperate gamble to split Allied forces and capture the port of Antwerp. The offensive's failure illustrated how American tungsten ammunition had shifted the tactical balance, even when German forces achieved surprise and initial success. The first days of the offensive, from December 16th through 19th, saw German armor achieve significant advances through American lines that were thinly held and unprepared for major assault. Panther battalions spearheaded the advance, overrunning American positions and destroying numerous Sherman tanks in one-sided engagements where German tactical surprise and armor superiority were decisive. These initial successes suggested that German armor, properly concentrated and employed with surprise, remained a formidable offensive weapon. But as American forces recovered from initial shock and began organized resistance, the familiar patterns reasserted in themselves. American artillery, vastly superior in quantity and fire control, began hammering German armor concentrations. Tank destroyer battalions moved to block key roads and engage German armor from prepared positions. Sherman companies equipped with 76mm guns and HVAP ammunition engaged Panthers under conditions that negated German advantages. The engagement at Krinkult-Rocherath on December 17th and 18th exemplified this shift. Elements of the 2nd and 99th Infantry Divisions, supported by tank destroyer and Sherman companies, fought a desperate delaying action against the 12th SS Panzer Division. German Panthers attacked aggressively, expecting to overwhelm American defenders through shock and superior armor. Instead, they encountered prepared defenses where American crews used buildings for cover, ambushed German tanks at close range, and targeted gun mantlets with HVAP ammunition. The two-day battle resulted in German Panthers being knocked out at ranges where Panther crews expected invulnerability. American after-action reports documented multiple instances of Sherman 76mm guns achieving frontal penetrations on Panthers at ranges from 200 to 600 meters. The HVAP ammunition proved critical in these close-range urban engagements where German tactical doctrine assumed Panthers would dominate through armor superiority. By December 24th, as German offensive momentum stalled and weather cleared to allow Allied air power to intervene decisively, the Ardennes offensive had effectively failed. German armor losses were catastrophic. Hundreds of Panthers and Tigers were destroyed, disabled, or abandoned when fuel supplies ran out. American forces had demonstrated once again that combined arms warfare, superior logistics, and effective anti-tank weapons, including HVAP ammunition, could defeat German armor even when Germans achieved initial surprise and concentration of force. The BAN, post-war interrogations of German tank commanders and ordnance officers, provided detailed insights into how the tungsten ammunition threat was perceived within German military circles. The interrogations, conducted by American and British intelligence teams in summer and fall 1945, revealed consistent themes across multiple sources that confirmed the impact of HVAP on German tactical thinking and morale. Oberst Horst Niemak, former commander of a Panther battalion in the West, described in his interrogation how knowledge of American improved ammunition affected crew confidence. His battalion had fought in France during August and September 1944, experiencing firsthand the introduction of HVAP-equipped Sherman companies. Niemak stated that crews who had previously trusted their frontal armor became noticeably more cautious after the first instances of Panthers being penetrated frontally by 76mm fire. The psychological impact extended beyond individual crew confidence. Niemak explained that platoon and company commanders began planning operations more conservatively, avoiding tactical situations where close-range engagement with American armor was likely. This defensive mindset reduced German effectiveness in fluid mobile operations, where armor needed to respond aggressively to tactical opportunities. The knowledge that American tanks could now kill Panthers frontally made German commanders hesitant exactly when boldness might have created tactical advantages. General Major Friedrich von Mellenthin, Chief of Staff for several Panzer armies during the war, provided strategic-level perspective during his interrogation. He described how German High Command understood by late 1944 that American industrial capacity had overcome most German technical advantages in weapons design. The tungsten ammunition issue exemplified this broader pattern. Germany had developed superior technology first, but could not produce it in quantities that mattered operationally. America had developed similar technology later, but manufactured it in thousands of rounds and distributed it to frontline units. Von Mellenthin stated explicitly that by early 1945, German planning assumed American forces possessed sufficient tungsten ammunition that any major engagement would involve HVAP-equipped enemy tanks. This assumption influenced operational planning, force deployment, and tactical guidance to units. German commanders could no longer rely on armor superiority as a decisive advantage. They needed to compensate through tactical skill, terrain use, and combined arms coordination, exactly the areas where American forces held advantages through superior training and overwhelming material support. The technical interrogations of German ordnance engineers revealed the frustration of professionals who understood the problem perfectly, but lacked resources to solve it. Oberingenieur Klaus Werner, who had worked on armor-piercing ammunition development at the Army Weapons Office, described the tungsten allocation decisions that prevented German production of sub-caliber ammunition in meaningful quantities. He explained that every request for tungsten for ammunition production was rejected in favor of machine tool allocations that were deemed more critical to overall war production. Werner stated that German engineers had developed improved tungsten core designs by 1943 that matched or exceeded American HVAP performance. But these designs never reached production. Test rounds were manufactured in quantities of dozens or hundreds for evaluation purposes. Full-scale production was never authorized because tungsten simply was not available. Werner estimated that if Germany had possessed American-level tungsten supplies, German industry could have produced 50,000 or more tungsten core rounds monthly across all calibers. But that capacity was theoretical, irrelevant, given material constraints. The interrogation of Dippel. Ing. Ernst Kniepkamp, who had been responsible for tank development at the Weapons Office, provided insights into how tungsten ammunition intelligence influenced German tank design thinking. Kniepkamp explained that reports of American HVAP in late 1944 triggered discussions about redesigning Panther turrets to eliminate or minimize the mantlet vulnerability. Several concepts were evaluated, including external mantlet designs that would have been more resistant to penetration and redesigned gun mounting systems that reduced the vulnerable area. None of these concepts advanced beyond preliminary sketches. By late 1944, German tank production was focused entirely on maintaining output of existing designs. No capacity existed for major redesign programs that would disrupt production. Kniepkamp stated that even if improved designs had been developed, implementation would have taken 6 to 9 months minimum, time that Germany clearly did not have. The tungsten ammunition threat was recognized, understood, and accepted as unsolvable within wartime constraints. The broader industrial context explained why Germany could not respond effectively to American ammunition improvements. By 1945, German industrial production was collapsing under combined effects of Allied strategic bombing, loss of territory containing key resources and manufacturing facilities, and severe shortages of everything from raw materials to skilled labor. The armaments industry that had supported German military operations through 1944 was disintegrating. The United States Strategic Bombing Survey, conducted after the war, documented the cumulative impact of Allied bombing on German tank and ammunition production. The survey found that by early 1945, German tank production had fallen to roughly 60% of peak output, despite desperate efforts to disperse manufacturing and maintain production. Quality control had degraded significantly as slave labor replaced skilled German workers drafted for military service. Component shortages forced assembly lines to halt frequently, sometimes for days, awaiting delivery of parts. Ammunition production suffered even more severely. The survey documented that propellant production had become a critical bottleneck by late 1944, with several key chemical plants destroyed or severely damaged by bombing. This affected all ammunition types, from rifle cartridges to tank gun rounds. Even if tungsten had been available for armor-piercing projectiles, propellant shortages would have limited production of complete rounds. The entire industrial system supporting German military operations was failing simultaneously across multiple bottlenecks that could not be corrected. American industrial production, by comparison, continued expanding through 1945. Tank production, ammunition manufacturing, and tungsten processing all maintained or increased output right through the war's end. The United States produced more Sherman tanks in 1944 than Germany produced tanks of all types combined. American ammunition production exceeded German output by factors of 3 to 5 depending on caliber, and American industry achieved this while simultaneously supporting Lend-Lease shipments to Britain and the Soviet Union that equipped entire armies. The disparity in tungsten ammunition production crystallized this broader industrial advantage. American factories produced specialized armor-piercing rounds, incorporating strategic materials while maintaining massive output of conventional ammunition, building thousands of tanks, manufacturing tens of thousands of aircraft, and supporting the largest amphibious operations in military history. German factories struggled to produce basic ammunition in sufficient quantities while watching tank production decline and facing shortages of everything from steel to explosives. The final months of the war demonstrated the consequences of this industrial disparity. German tank units fought with increasingly desperate tactics as fuel shortages, ammunition shortages, and mechanical breakdowns reduced operational capability. Panthers were abandoned after minor damage because no spare parts existed for repairs. Tank units operated at 20 to 30% strength, not because tanks had been destroyed in combat, but because they could not be maintained or fueled. The sophisticated weapons Germany had designed with such care became useless for lack of the industrial support needed to keep them operational. American armor, supported by functionally unlimited logistics, pressed attacks continuously across all fronts. Sherman tanks that were damaged in combat were repaired within days or replaced immediately from reserves that seemed inexhaustible to German defenders. Ammunition of all types, including HVAP, flowed forward in quantities that ensured American crews never faced shortages. Fuel, spare parts, and maintenance support allowed American armored units to sustain offensive operations that German forces could not match even when German equipment was technically superior. The testing at Kummersdorf, that had begun in October 1944 with examination of captured HVAP rounds, had documented precisely what American tungsten ammunition could achieve against German armor. The data was comprehensive, accurate, and operationally useless. German industry could not counter the threat. German tactics could only partially mitigate it. German tank crews would fight the remainder of the war knowing that enemies possessed ammunition that negated carefully engineered armor advantages that had cost Germany enormous industrial effort to achieve. The irony was profound and bitter. Germany had pioneered tungsten core ammunition years before America. German engineers understood the technology completely. German metallurgists had developed tungsten carbide materials that matched or exceeded American specifications. But German industry could not produce the ammunition in quantities that influenced battlefield outcomes. American industry, starting with less knowledge and developing the technology later, nevertheless manufactured tens of thousands of rounds and distributed them widely enough to affect tactical calculations across entire theaters. This pattern repeated throughout German weapons development in the war's final years. Germany developed advanced jet aircraft, but could not produce them in meaningful numbers or train pilots to fly them effectively. Germany designed sophisticated submarines with advanced capabilities, but built too few too late to influence the Battle of the Atlantic. Germany created powerful tank guns and thick armor, but could not supply the ammunition or fuel needed to make them effective. Technical innovation without industrial capacity to implement it proved strategically worthless. The final collapse of German resistance in April and May 1945 brought the practical questions about armor and ammunition to an end through Germany's complete defeat. American armor equipped with HVAP ammunition had contributed to that defeat, but the ammunition itself was only one factor among many. Superior numbers, overwhelming logistics, total air superiority, and better operational doctrine all mattered more than any single weapon system or ammunition type. But the HVAP story illustrated fundamental truths about industrial warfare that shaped military thinking for decades afterward. Technical quality mattered less than production quantity when disparity was sufficiently large. Industrial capacity to respond to tactical problems mattered more than initial technical advantage. Access to strategic materials like tungsten determined which innovations could be implemented at scale and which remained laboratory curiosities. These lessons, learned at terrible cost during World War II, influenced Cold War military planning and continue informing defense industrial policy today. The German engineers who had tested American tungsten ammunition at Kummersdorf in October 1944 understood all this clearly. Their meticulous testing documented exactly how American industry had solved the Panther armor problem. Their comprehensive reports explained precisely what the implications were for German tactical operations. Their professional competence was never in question. What they lacked was not knowledge but capacity, not understanding but resources, not skill but time, and materials to implement solutions they could design but not build. The tungsten ammunition story represents one of the smaller technical details of World War II, far less dramatic than great battles or strategic campaigns. But it illustrates perfectly the industrial realities that determined the war's outcome as certainly as any battlefield victory. Germany entered the war with technical advantages and lost them through industrial attrition. America entered the war with industrial advantages and leveraged them into technical solutions that German industry could not match. The neat holes punched through Panther mantlets during testing at Kummersdorf proved what the statistics already showed. Industrial capacity would defeat technical sophistication when disparity was as great as America versus Germany represented. The post-war world absorbed these lessons thoroughly. The Soviet Union, observing American industrial performance during the war, restructured its entire armaments industry to prioritize mass production over technical elegance. The United States institutionalized industrial mobilization planning and maintained defense production capacity far beyond immediate peacetime needs. NATO planning assumed that industrial capacity to support sustained operations mattered more than initial equipment superiority. The Cold War became as much about production capacity and resource access as about weapons technology. Modern military procurement continues wrestling with the same tensions between technical sophistication and production capacity that World War II illustrated so clearly. Advanced weapons systems with impressive specifications but limited production numbers versus simpler systems that can be manufactured in quantity. Specialized materials that enhance performance but constrain production versus conventional materials that allow mass manufacturing. These trade-offs, fundamental to military planning, were crystallized in the tungsten ammunition story, where German engineers possessed the knowledge but lacked the tungsten. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.